Hello and welcome back. This is the second lecture on special relativity. In the last lecture, we saw that to translate observations of the physical world between different observers, we need to establish a dictionary. Now, establishing this dictionary is always possible for any sets of observers. However, for a special class of observers, so-called inertial observers, Newton's laws always appear to be valid. These observers appear to be moving with respect to each other at a constant velocity. That is, they have uniform motion with a constant speed as well as constant direction with respect to each other. More importantly, there appears to be no preferred inertial observer. All of these observers are equivalent. That is, there is no preferred rest frame of the universe. This idea seemed to fit quite well with this Newtonian way of thinking. However, towards the end of the 19th century, it became quite apparent that this transformation, this dictionary of Galilean relativity, which appeared to be consistent with Newton's laws, did not fit in with Maxwell's equations. This led to a paradox, and we will see today how Einstein thought about this paradox and puzzled over it. So here's the plan for today. We'll begin by talking about the relationship between Maxwell's equations and Galilean relativity, and we'll see exactly where the conflict is between Maxwell's equations and Galilean relativity. Attempts to resolve this conflict resulted in an experimental test which was the Michelson-Morley experiment. And we will see that the results of the Michelson-Morley experiment were quite counterintuitive to what physicists expected at the time. This led to a paradox where Einstein began to puzzle over this result, or what was a null result of the Michelson-Morley experiment, and we will see his thought process for how he began to resolve this paradox. Observers, for consistency with what we're going to do later, so we'll call this first observer, observer S, and this observer as S prime. And what we saw is, if the distance between these two origins is changing with time, these observers are moving with respect to each other at a constant velocity. So this distance is, let's say, some v relative times time. Time is measured either by the first observer or the second observer. Okay, so now if you take these two different observers and you look at any particle and you ask what its speed is, so let's say the speed as measured by observer S is, and let's write the speed here as Vs. This is the speed measured by observer S. Now the speed as measured by observer S prime would be Vs prime, and the relationship between these two would be Vs prime would be Vs minus Vr. Okay, if these are vectors, then you would take into account appropriate vector signs. What this tells me is that since the observer S prime is moving to the right, this object should appear to be moving slower with respect to observer S prime. So now here's the conflict, or here's the worry, which is if I look at Maxwell's equations, it's telling me that there is some speed c with which light waves travel. But from the principle of Galilean relativity, so this here is from Maxwell's equations. and this is from Galilean relativity, which is consistent with Newton's laws, we see that all speeds and all velocities are observer dependent. So if the velocity as measured by one observer is Vs, the velocity as measured by the second observer will be Vs prime. And for simplicity, let's just suppose that everything is moving along one direction, let's say the x direction. So what this means is, if I have a particular observer, S, who is, let's say, at rest, they see light moving to the right with a speed c, and you now have a different observer with S prime, who is moving to the right at a speed vr relative to the first observer. What you would expect is that the speed of light as seen by this second observer would be some c prime, which would be related to the original speed by c minus vr. Okay, that is, they would see a reduced speed for the speed of light. Now, in Galilean relativity, we have no way to pick a preferred observer. At least Newton's laws don't allow us to pick a preferred observer. Okay, so the question is, Maxwell's equations tell us that there is a speed c. So Maxwell's equations tell us that there must be a preferred observer or rest frame with respect to which the speed of light is that constant c. Okay, at least this was the thinking at the time. And therefore Galilean relativity holds. Okay, so the assumption is Galilean relativity holds, and different observers who are moving at different speeds will see a different speed for light. But there is one particular observer who measures the speed of light to be c, which is the speed in Maxwell's equations, and they become that preferred observer. Okay, so Maxwell's equations tell us that there is some particular reference frame or some particular inertial observer who is the preferred inertial observer. So this reference frame, this preferred reference frame, was called the ether.